Okay, so welcome back everybody. So I've gone ahead and opened all of the cells for pre-processing in EDA. If you're walking through this with me, this is what yours should look like now. So the reason we check the data types right up front is many times during pre-processing, we have to do some heavy lifting and do some typecasting here because, as you know, a machine learning algorithm or any type of algorithm really doesn't have a value to assign to a word if a character or a string or something like that is in your data set, right? We don't have that type of problem. If you go back up here and we look, we have time of day, air temperature, humidity, dew point, barometric pressure, and solar radiation in the sample there, and we're not worried about anything other than the numbers there. And we need to get everything to a number. So even if it's a word or a series of words or a series of categories in this particular section, we would have to convert that over to either a column with numbers in it or a series of columns that would have binary numbers in it. So you can dive a little bit deeper into that if you have that situation, if you're working along with a different set of data or something like that. You can dive into label encoding and one hot encoding. There's two different ways to convert strings and characters over to something that's useful for modeling. We don't have that. Everything we have is in a numeric format. Doesn't matter right now whether it's ints or floats. Everything's good. We're not getting into the efficiency of modeling or memory or anything like that. We just want everything in a number. Also, we're going to check for any missing values. We don't want missing values in our data. We can do a quick is null here to check. We don't have any missing values, so we're good to go. As we mentioned earlier, we've got to convert air temp and dew point over to Fahrenheit degrees, so we know what's going on. And then last but not least, we pull a quick describe on our data frame. That takes all of our numeric variables and shows us descriptive statistics. This is a great place for you to think about things like distribution, mean, standard deviation, or is one side of the data skewed more than another. We won't get into those things here in this exercise because this is a very introductory exercise. Just know as you get deeper into this, those things matter tremendously when it comes to modeling, and a lot of what we do as ML engineers and data scientists is move this data around. We transform a lot of it to get it into the appropriate format so models can actually be very sensitive to it. Quite often we don't just leave it in the format that it comes in to the notebook with. So recognize that there's a lot of heavy lifting there still done to do. Correlation as well, I mentioned this in the last video, right? We're really studying the features, the relationship between the features. If you are unsure what correlation is, dive into Pearson's correlation coefficient online. It'll give you everything in the world that you need to know. Basically, in this particular regression problem, we look at correlation because we're trying to identify features or the X values that are highly related to one of those, to one another. You see solar radiation sitting out here on the end, right? But you've got situations like this intersection between dew point and air temp where you got a 0.82 correlation here, where correlation only runs from -1, being strongly negatively related, to +1, which is strongly positively related. You want to be careful when you have X values that are strongly related to one another because they may actually impact the model. You may get some feature bias into the model and it actually learn that particular rule, if you will, more than others, or treat it with a stronger priority more than others. For this particular exercise, we're not worried about that particular problem. It's called collinearity, if you'd like to go look it up, but we're not necessarily worried about that. We're just looking at the correlation, taking a note of correlation itself, so you can dive a little bit deeper into it in the next exercise. So let's get into the modeling. That's what this video is about. And again, I'm going to treat it the same way as I did the last exercise. So I'm not going to run any of these cells until the next video. So the first thing we have to do is split our data up. Now, why in the world do we need to split our data? We've got this really nice data set here, really nice spreadsheet full of 7 variables. 6 of them we're going to use for inputs, and 1 of them, solar radiation, that we're going to use for output. Why do we need to cut it up? Well, we actually need to split it up because a big part of machine learning and using an algorithm to find the patterns or the relationships between the features and the related outcomes, a big method that you actually do in order to solve that problem is called training. And you have to use a large amount of the data. Remember, this is historical data. You give it to the algorithm, you apply the algorithm, or you fit the algorithm to the data, and it does what it's supposed to do. That process is called training. Well, if we're going to train the algorithm, we also need to be able to assess how good that training was. So we have to have a piece of the data that wasn't used for training to actually test the algorithm to make sure that it's training appropriately and can generalize or be used on other data with the same structure, the same variables, right? If it doesn't pass the training process, then we either have done something incorrectly to the data, might be using the wrong algorithm. In the end, machine learning might not be the right thing. Machine learning doesn't solve everything, right? And sometimes you have to weigh the costs and the benefits of these problems. Sometimes there's so much that you have to do to the data that machine learning all of a sudden doesn't become a viable problem. Not going to be the case here. So we're going to split this data up into a separate set of values. One are just the X values. We've identified those. We can go actually up here. Just the X values are time of day, air temperature, humidity, dew point, and barometric pressure. We're going to just use those for training. Remember, the algorithm is trying to find the relationship between those 5 variables and the outcome, right? That's what it's trying to find. So we're going to separate the X values, or the features, from solar radiation, and we're going to call the X values X values, and we're going to call solar radiation, that single column out there, just a Y value. And something I like to do from time to time is just do a quick, just run a quick head on my data just to make sure that it came out right and that my slicing has selected what I want it to. You don't want to, as a newbie, what you'll wind up doing is you'll accidentally slice too much and you'll stick your outcome into your training data. And you'll train a perfect model every time because your outcome and your training and your features are sitting in the actual X values together. So it's always good to kind of prove this out and take a look at it. So the training process comes in like this. We're just going to use this neat method called train test split. This is a function that is in scikit-learn. We're going to pass our X inputs and our Y output to it. We want a test size of 30%, which will give us 70% of the data for training. And since this is going to randomly stratify this data to make sure that it's not ordinal or something like that, or something like time of day really doesn't screw with it because it's in a certain order, we're going to pass a value called random state to the train test split, and that's going to ensure that not only is our data randomly stratified, but every time we run this, it's randomly stratified the same way. The outcome of that is actually 4 variables. 2 that we're going to use for training. We've got an X train, we've got a Y train, and then 1 that we're going to use to make predictions, and then this one is going to serve as the holdout for ground truth. So last but not least, we're going to go ahead, now that we've got the data in the format we need, we're going to go ahead and instantiate our decision tree regression algorithm out of scikit-learn. Since this is a quick exercise, we're going to limit it to building a decision tree that is only 5 levels deep. And we haven't talked about decision trees. That's the first time you've heard it. There's some more information in the resources about how they work, and we'll look at them here in just a few minutes when we plot them out. Just know that's sort of the basic type of of supervised machine learning algorithm that usually everybody starts with. Has been around for, goodness gracious, 60, almost 70 years now, really before we had any type of machine learning. And it's always good to start there with a really simple algorithm that you can make sense of, right? And like I said, at the bottom of this notebook, I've listed some additional resources and another presentation that I built about how decision trees work. So you can go in and get as mathy as you want and geek out on it, like I always do with algorithms, but we just don't have time for it in this exercise. So after we instantiate or just bring in a copy of that, an instance of that algorithm, and we're gonna this is sort of the knob and the dial that we're gonna control how long it runs and how much information it uses. We're gonna actually fit it, and this is where the training actually happens. And you see we're assigning that to a variable called model, so it's easy to keep up with. And we're passing our training data to it. These are features, and these are the related outcomes of those features. So that's our train test split. That is building our first classification model. And then last but not least, we're going to take that model and apply it to the test set of features that it was not trained on and make predictions. And what that's going to allow us to do is it's going to give us a single column of predictions and a single column of known values from the same features. And that's your your Y test. This is what we always call ground truth. We know what these values are. These are predictions. And we're trying to compare these two values when we assess a model. We'll get into that in the next exercise. Talk to you in a second.